This presentation is to describe the concept of reverse contrast that we've recently introduced in Doppler holography to be able to perform retinal blood flow imaging at a much lower frame rate than before. The motivation for this is quite straightforward. We are now able to realize these nice blood flow movies in the eye fundus, but it's not done in real time. It's done with an ultra-fast camera. And it would be very helpful for clinicians to have an instrument that works in real time. The thing is that the Doppler frequency shifts in the retina, they can be up to 30 or 40 kilohertz. Thus, we need a camera with the corresponding sampling frequency to be able to sample it properly. But these cameras happen to be working offline, and they are ultra expensive and they generate ultra large amount of data. So how can we do it without this ultra fast camera? And that's where this reverse contrast comes in. The idea of this reverse contrast is to take advantage of the symmetry of contrast between low frequency power Doppler images and high frequency power Doppler images. In this movie, where power Doppler images are shown for different frequency ranges, you see that at ultra low frequencies, vessels are darkly contrasted, and then as the frequency increases, you start to see small blood vessels and then bigger blood vessels, until at high frequencies you only see large vessels with a bright contrast. And that is these ultra low frequencies power Doppler images that we want to use in reverse contrast, because they are able to show vessels with a dark contrast. At low frequencies, you then see the small blood vessels that appear with a bright contrast, and you see the lumen of the large retinal vessels still with a dark contrast. And at high frequencies, you see retinal blood vessels with a bright contrast only. And there is a symmetry between these ultra low and high frequencies power Doppler images that we want to use, because if you just reverse the contrast of the ultra low frequency image, then you're able to obtain something similar to what you have at high frequencies. And it's very advantageous if we're able to do that, because then we can lower the sampling frequency of the camera. We don't need a very high sampling frequency to access the lower frequency content. So here we were using camera sampling frequencies between 10, 20, 39 and 75 kilohertz. And if we look at the 1 to 3 kilohertz power Doppler images, they are similarly contrasted, at least qualitatively. So why exactly are power Doppler images showing vessels with a dark contrast at low frequency? Our explanation is based on energy conservation. So here we are considering power Doppler images for high frequency ranges. So here it's 6 to 33, and the ultra low frequency range 0.2 to 1 kilohertz. And if you represent schematically the power spectrum density of the light scattered in either blood and tissue, it will look something like this. So at high frequencies, of course, the power spectrum density is greater for light scattered in blood, because there has been more Doppler frequency shift of large frequency shift. So there's more Doppler broadening, there's more energy. This is the reason why the power Doppler image for high frequencies show vessels with a bright contrast, because when you integrate this quantity, it leads to a brighter contrast. And reciprocally, what we see here is that if the energy is shifted toward higher frequencies for light scattered in blood, then it means that there is a depletion of energy at low frequency. Thus, the power spectrum density of light scattered in tissue is greater, and thus vessels are darkly contrasted because the power Doppler is lower. So we say it's energy conservation because each pixel of the field of view has received the same illumination, the same energy from the laser, and this energy should correspond to the total area under the power spectrum density curve. And it's something that should be conserved. So if there is more energy at higher frequencies, it means that there is less energy at low frequency. And thus there is a symmetry of contrast between the content of low and high frequency power Doppler images. So let's reverse the contrast of some images here. So here we still have our 0.221 kHz power Doppler image. We reverse the contrast and we compare it to the 6 to 33 kHz power Doppler image, and we see something very similar. It's not identical because there are some areas in this example that we've chosen for that where in the vicinity of the optic nerve there was a piece of RPE that was absorbing a lot of light. Thus on the image of the right it appears dark because light is absorbed, and on the image from which we have reversed the contrast it appears brightly because it was previously dark because of absorption, and then it becomes brighter after the reverse contrast. But apart from that, the images are near identical, and it means that it's working at least good enough for the vasculature. Now, you might be thinking that it's just because of absorption that vessels are seen with a dark contrast on these images, and we can say it's not really the case, because when we integrate the total power spectrum density, which is the quantity that gives us the image that gives us really the absorption, we see that absorption takes place where there is the RPE absorption, but vessels where there is also a bit of absorption because of the red cells absorption are not as well contrasted on the image on the right than the one on the left, which means that on the right it is pure absorption, and on the left there is something else that is the reason of the dark contrast. And what I'm trying to demonstrate in this presentation is that the reason of this dark contrast is actually the depletion of energy, because the spectral energy has been shifted toward higher frequencies. So let's make a proof of concept at 67 kHz of this reverse contrast measurement. We take again the 6 to 33 kHz range, and then we take the 0.224 kHz range, this time in reverse contrast, and we look at the variations of power Doppler for both of these ranges, and we see that in the artery and vein we've chosen exactly the same areas, and what's nice is that it's the same data, so and that we choose to process in one way or the other way, and we find variations that are very similar for both ranges of power Doppler. And what it means is that these negative variations of low frequency power Doppler reflect the positive variations of high frequency power Doppler. So that might sound a bit obscure, but it can be very well understood when looking at the spectrogram in the artery and vein of the corresponding region of interest. What you see is that over the course of cardiac cycle, the energy is shifted toward greater frequencies, for example during systole when blood flow is accelerated, and that is the red part on the spectrogram. And when the energy is shifted toward greater frequencies, it means also that the shift can be observed at lower frequencies, because there is a depletion of the energy that used to be at low frequency. So the blue thing in the spectrogram reflect variations of the red part of the spectrogram, whether it is in the artery and the vein. And that is this low frequency depletion that we are using in reverse contrast to make blood flow variation measurements. So here are the corresponding blood flow movies for these different frequency ranges, and what you can observe is that it's working well enough for large retinal vessels. There you see qualitatively the same variations on the left and right movies, but there are some vessels that appear with a dark contrast on the movie on the left, and we have a fix for that I will describe later. But now the question that we need to answer right now is more would this actually work with a real low sampling frequency? Because in that case we have aliasing. If we're making the measurement at 67 kilohertz, we're separating the different contributions, but if we are making a measurement at 8 kilohertz to access the 0 to 4 kilohertz range, we have everything else that is aliased and might cause some issue, especially with the assumption of energy conservation. And the answer is that it seems to work. Here is a measurement at 8 kilohertz, and we are once again looking at the reverse contrast over the 0.2 to 4 kilohertz range, and we are able to nicely sample the blood flow variations in the vessels. So in these measurements we looked again at the variations in an artery and a vein, and we were able to obtain what would have been expected from such measurement. We find the same waveform profiles as we do at high frequency. When we represent the coefficient of variation map, we are able to differentiate arteries and veins in red and blue also. So we are able to make blood flow measurements of sufficient quality, for example, to assess the resistivity index, or maybe eventually to measure the propagation of the pulse wave. And that can be understood, remember, by the depletion of energy that we can still observe on this spectrogram that are plotted for this data for the same regions of interest. You see that over the course of cardiac cycle, you have during the systolic the peak, the energy that is shifted outside the camera bandwidth. Now we can only access the only the 0 to 4 kilohertz range. So what's happening exactly when this energy is shifted outside the camera bandwidth? Well, when the camera is working, it's has an exposure time, and it's integrating all of the signal variation during that time, and this corresponds to a sampling that is a Dirac convoluted by a rectangular function, so it's a zero order hold. And in time domain, this is what it looks like, and in frequency domain, now the convolution becomes a product, and the rectangular function becomes a sinc function, a sinus cardinal function, which has a frequency response that allows to sample what is in the Nyquist domain and attenuate a bit what is alias. So there is an attenuation of the alias frequencies, and I imagine that is what allows this scheme not to be neutralized by the aliased frequencies. So I started the presentation by showing a composite blood flow movie where that we obtained at very high frequencies, where we put in cyan, we encode the lowest frequencies that reveal the slowest flow. So usually we put 1 to 6 kilohertz, and in red we put the high frequency content, so usually the 6 to 33 kilohertz. And when we combine those, we have a nice image that is able to differentiate arteries and veins in the choroid, for example, or very fast flow in the retina, so the lumen of retinal vessels appear red. Now, what we can do with a measurement at low frequency is that we can still access the low frequency content that reveal the slowest flow. It's not a problem. But then to obtain the fast flow, instead, because we can no longer access the very high frequency content, we use the ultra low frequencies, and we reverse the contrast, and we obtain something very similar. So when we do the composite image, once again we are able to retrieve the same contrast, and these images are also able to differentiate arteries and veins in the choroid. So here are a few examples of what we can do with low frequency Doppler holography. We're able to nicely reveal the smaller blood vessels with the positive power Doppler at low frequency. And then thanks to this reverse contrast scheme and the red part of the image, we're able to reveal the gradient of flow in the large retinal vessels and perform this arteriovenous differentiation in the choroid. We are able to do so with a good temporal resolution. So here is the corresponding blood flow movies for the two measurements that were performed at 67 and 8 kHz, and you can see that the signal to noise ratio is comparable. It's not exactly as good on the movie on the right, but it's quite good compared to what we were expecting. So we are left with a question here, how well can LDH work at a few kilohertz as what it can do at 75 kilohertz? So we've demonstrated that we can do similar quality of perfusion maps, of flow variations, and of this low flow, high flow maps. The quality is not exactly the same as at very high frequency, but it's surprisingly good considering how undersampled the signal is, and it's sufficient for clinical use. So here is an example of a pathological case of blood flow image in reverse contrast at 10 kHz, and you can see that we are able to nicely reveal this pathologically decreased blood flow and blood flow in the retina and choroid very nicely. So to summarize the different concepts that I talked about in this presentation, there was the energy conservation that explains why vessels are darkly contrasted at low frequencies. If vessels are brightly contrasted at high frequencies, they will be darkly contrasted at low frequencies. Low frequency measurements contain the information of both the slow flow and the fast flow. So to reveal the slow flow, it's the usual positive contrast, and the fast flow is revealed with this negative or reversed contrast, which allows us to realize these composite movies from the same data. And we are able to measure the variations of blood flow in reverse contrast thanks to the shift of spectral energy toward higher frequencies that induces a depletion of energy at low frequency. So in conclusion, this reverse contrast approach allows blood flow imaging of Doppler frequency shifts that are largely beyond the Shannon-Nyquist sampling limit. The key measurements of high-frequency Doppler holography can be retrieved with reverse contrast, low-frequency Doppler holographic measurements, so these perfusion maps, slow and fast flow color composite movies, and the monitoring of blood flow variations. Reverse contrast low-frequency Doppler holography is of sufficient quality for a relevant clinical use, and this makes Doppler holography realizable in real time in the near future, because 8 or 10 kilohertz is something that is a camera frame rate that will be reached in real time in the near future. And to finish, here is an example of what can be achieved in real time with Doppler holography to this day. It's at 5 kilohertz, which is not quite enough to properly capture the blood flow variations over cardiac cycles, but it's starting to show something very, very nice. And I imagine that in the coming year, we will be able to have something that works in real time. Thank you for your attention.